Welcome to the video for Lecture 16, Section 2. This video is on strain gauges. Strain gauges are used to measure strain and find the stresses that materials experience using the stress-strain relations discussed in the previous video. Strain gauges are also used in other sensors including load cells, pressure sensors, and torque sensors. Strain is defined as a change in length per unit of initial member length. Strain can be either tensile, where the member becomes longer and thinner, or it can be compressive, where the member becomes shorter and thicker. Strain can be measured using piezo-resistive materials, carbon-resistive, and bonded metallic wire. Piezo-resistive materials came out of the semiconductor industry. They are materials in which the resistance changes when the material is subjected to either a stress or strain. The slide shows two strain gauges with several parts labeled. The gauge to the left, the black and white one, is mounted to measure strain in the horizontal direction. The gauge to the right, the yellow one, is mounted to measure strain in the vertical direction. The strain direction aligns with the active grade length and the primary gauge axis. The term bonded describes the fact that the gauge material used to make the active grade is mounted on a backing. Both the backing and the gauge are mounted to the surface at the point that we want to measure the strain. The alignment marks are used to place the gauge over the point where you want to measure the strain. The gauges are aligned to measure strain in the primary direction of interest. The strain reading will be an average over the entire active grade length. Also notice the solder tabs. This is where small wires are soldered to the gauge so that the change in resistance can be measured. The grade lines are like wires, and in some cases are actual wires. The grade lines get thinner when the active grade length is stretched due to a tensile strain. So, in tension, the resistance is the initial resistance plus a change in resistance called delta R. In compression, the grade lines get fatter or thicker when the active grade length is compressed due to compressive strain and the resistance is the initial resistance minus the change in resistance. Again, if the grade gets thinner due to tensile strain, the electrical resistance of the gauge increases. If the grade gets thicker due to compressive strain, the electrical resistance decreases. The relation between change in resistance and strain is given by the gauge factor of the strain gauge. The gauge factor, capital F, equals delta R over delta L over L. The denominator delta L over L is the definition of strain, so the gauge factor equals delta R over the strain given by lowercase epsilon. Strain gauge manufacturers give us the gauge factor and the initial gauge resistance. We measure the change in resistance, delta R, and can find the strain that caused the change in resistance. Conventional foil bonded strain gauges have gauge factors from 2 to 3.2. Piezo-resistive materials have gauge factors from a minus 150 to 200. The high sensitivity of piezo-resistive materials comes with a disadvantage. The materials are highly temperature sensitive. If you remember, most of data loggers can measure voltages, but they cannot measure resistance and changes in resistance. To convert a small change in resistance to a change in voltage that we can more easily measure, we will use Wheatstone bridge circuit. I will talk about Wheatstone bridge circuits next time. Here is a list of strain gauge selection factors. The next few slides will discuss each factor in more detail. Gauge length is important because strain gauges will give you the average strain over the active grid of the strain gauge. So, if you want more of an average strain, you might choose a longer strain gauge. If you want a peak strain at a point, you will want to choose a shorter strain gauge. Longer gauges are easier to handle, and they dissipate heat better than shorter strain gauges. Typical strain gauges lengths are shown on the slide for conventional bonded gauges and for piezoresistive gauges. Strain gauges can be made using different alloys. Here are 3 common alloys with comments about strengths. Single strain gauges measure the strain along the primary axis of the strain gauge. Sometimes you want to know the strain in 2 or 3 directions. You can buy gauges that have 1, 2, or 3 gauges. A strain gauge with 2 or 3 directions are called rosettes. When specifying strain gauges, you can specify the length, which we have talked about already, and the width. Wider gauges average the strain over the total length and width of the active grid. In the previous slide, it was noted that a single gauge measures strain in one direction, along the primary axis of the gauge. But sometimes you want the strain in all 3 directions. To measure strain in 2 or 3 directions, you need to use rosettes. There are 2 general types of rosettes. Stacked rosettes put 2 or 3 gauges on top of each other. Stacked rosettes can have a smaller footprint so they can find a more localized peak strain. But they tend to have heat dissipation problems. Each gauge will have small current going through it, and the current will generate heat and an apparent strain. The other rosette type is called a delta rosette. The gauges are side by side. They have fewer heat dissipation problems, but delta rosettes do not measure strain at exactly the same point. Here are figures that illustrate stacked and delta rosettes. Stacked rosettes have the strain gauges stacked one on top of the other, and they measure strain in localized point. Delta rosettes are side by side, so the strain is not exactly at the same point. Strain gauges come with different initial gauge resistance. Typical initial resistance are listed here. Gauges with lower initial resistance are less expensive. Gauges with higher resistances will have less self-heating and apparent strain, are less sensitive to lead resistance, and have better signal-to-noise ratios. The self-heating that strain gauges have is the same self-heating issue that resistance temperature detectors have when connected to a Wheatstone bridge circuit. In the previous video, near the end, I mentioned the temperature coefficient of linear expansion. We know from the concepts associated with resistance temperature detectors that resistance depends on temperature. The heat generated by excitation signal of the Wheatstone bridge circuit will induce an apparent strain due to thermal expansion. Care must be taken when using strain gauges to prevent the gauge from being heated too much. Strain gauge heating can be managed by selecting gauges with less temperature sensitivity and a higher initial resistance. Many gauges now come with some self-temperature compensation. Another way to reduce apparent strain due to self-heating is to not exceed the maximum excitation voltage. Strain gauge fatigue life describes how many times a strain gauge can be strained and unstrained before the gauge has a permanent change in the unstrained resistance of 100 microstrain or more. The permanent change in the unstrained resistance is also called a zero shift, and it typically occurs around a million strained unstrained circles. Fatigue life is important for strain gauges used in other sensors and permanent installations. Strain gauges have strain limits. Again, strain is the change in length per unit initial length. Piezoresistive gauges have the lowest strain limits, less than 10,000 microstrain. The three biggest strain gauge errors to be on the lookout for are listed here. Strain gauges can be easily damaged during installation. A quick check of the initial resistance is one way to check the installation. Noise can be an issue. Shielding the leads and using filters can help manage noise. The apparent strain due to gauge heating can be a problem too. Apparent strain is managed by using compensating gauges, selecting gauges with higher initial resistance, and using the minimum excitation voltage possible. Before I wrap up this presentation, I want to talk briefly about load cells. Many load cells have strain gauges inside of the load cell, and load cells are used widely to measure force, weight, and mass. Load cells come in lots of sizes and shapes and are very rugged. Here is a little sketch from a local cell supplier that shows load cells being used to automatically measure the amount of material in the two containers. This sketch from a load cell supplier shows a load cell being used to weigh the number of products that go into each bag. This slide summarizes some of the highlights of this video. This brings me to the end of Lecture 16, Section 2 video. Write down any questions you have and bring them up in the class or lab. Thank you.